Hello everyone, and we are going to have another webinar conducted by Institute of Physics Sri Lanka. Thank you for being here today also. We have been organizing this monthly webinar series to promote physics and its applications and aware the public on hot key topics related to physics. So today's webinar, we have invited well-experienced research in material physics. It's Professor Ranjith Divigalpitiya, Research Professor, Department of Chemistry, Western University, Canada. We'll talk on physics of two-dimensional materials and applications. On behalf of IPSL, I would like to warmly welcome Professor Ranjith Divigalpitiya. Thank you, Professor, for accepting our invitation. Before we start the presentation, I would like to call upon Dr. Chathuri Nupayarachchi, co-editor of IPSL, to introduce today's resource person. And also today, session will be moderated by Professor Pitigal. Thank you very much, and over to Dr. Chathuri.
Thank you so much, sir. And privilege to welcome our resource person today, Professor Ranjith Divigalpitiya. So I'll tell you about him. From Two-Diamentional University back in 1978, and he obtained his MSc and PhD from University, Canada. He became an assistant lecturer in physics at Two-Diamentional University from Canada as a fellow, research associate, and visiting assistant professor in the Department of Physics at Simon Fraser University, Canada. He also in 1990 became a visiting scientist for 3 companies in the USA. But he also his time from 1992 to 2019 as senior physicist. Corporate R&D Laboratory in Canada in London, Ontario. From 2020 to up to date, he is an adjunct research professor in the Department of Chemistry, Western University, Canada, and is also Chief Scientific Officer in Hydrograph Clean Power Incorporation, Vancouver. His research interests include digital X-ray imaging, electrically conducting adhesives, UV photocatalysis, force sensors, photovoltaics, water purification, sensors for contaminants in water, lithium-ion battery materials, and nanoscale coatings. He will describe his long-term interest in applications of two-dimensional materials, leading to both new process and product development. His work has resulted in 190 invention submissions at 3 company and 20 patents, ladies and gentlemen. Now he is fully engaged in R&D on graphene-related applications with Hydrograph Clean Power Incorporation, which is an innovative graphene company in Canada. This webinar platform is over to you, Dr. Ranjith. Over to you. Thank you so much.
Thank you, Dr. Nupayarachchi, I think, for that introduction. Hopefully my sound comes through clearly. There were some issues earlier. Can you hear me well?
Yeah, yes.
Yeah. Okay, thanks. Yeah. So it's a great pleasure to present this webinar to you. It's pretty exciting topic for personally, but hopefully I can convey some of that excitement to you as well. So I think I've been working in this field on and off for quite a while, and I really thank the IPSL for giving me this opportunity. So the topic is physics of two-dimensional nanomaterials and application. So it's a pretty, I think I'll discuss these things at a higher level, not lots of detail, but to get some general idea about the area. So I think the plan is, let me make it bigger. I don't know, is that better? So I'll give you some, very short introduction to some of the terms that we will be using and discuss some of the structures and properties of this two-dimensional materials, and say something about graphene and graphene related materials and their commercial applications. And the last part of the talk, I'll touch on some graphene production techniques and this newly developed synthetic detonated graphene from hydrograph. So hopefully this will give you some idea about this area. So I know we're all physicists, we know about the nano. When you say nano, it's 10 to the minus 9, but it's still worthwhile to take look at how does it relate to the ordinary day-to-day objects. So if you start from 1 meter length scale and go lower, an order of magnitude by order of magnitude, you reach the nano level, and it turns out most of the things that are in the nanoscales are biologically originated materials, like viruses and the DNA material. So that's where we will try to work. And when we say two-dimensional materials, what I mean here in this talk is at least one dimension is much smaller than the other two dimensions, and the smaller dimensions is in the nanoscale, which is traditionally taken as less than 100 nanometers. So this geometry and this length scale impart new and sort of very interesting, useful properties to these materials. I'm pretty sure you know most about these things, but it's still interesting. And most of the materials come from, at least it used to come from, something called layered materials. So these are three-dimensional crystalline material, but they are ordered in layers. So you can, under certain conditions, you can break this 3D material into 2D constituent layers, either molecular layers or atomic layers. And that process is called exfoliation. It's almost like tearing pages out of a book, sort of that's the physical analogy. But so you will hear these terms, the exfoliation is used to make different 2D materials. So there's very large number of nanomaterials, and this sort of view graph shows some of the obvious and common materials. And as you know, the graphene is the sort of the poster boy for all the 2D materials these days, which is one atomic thick carbon, but it's arranged in a hexagonal array of atomic arrangement. And it has very extraordinary properties because of the nature of the atoms as well as the geometry. But another pretty large class of two-dimensional nanomaterials are what's known as transition metal dichalcogenides. So there's a pretty large amount of transition metals combining with sulfur, selenium, and tellurium, which is known as chalcogen, makes pretty stable compounds called MX2. They are also arranged in layered atomic arrangement, where you have within the layer covalent bonding, but between the layers very weak van der Waals bonding. Like graphite, which is the parent compound or parent material for graphene, the interlayer bonding is very weak. So it allows you to use that as a lubricant because it can shear really well atomic layers, and you can take them apart as well. And after the discovery of graphene, very large class of another around same in the periodic table, some of the atoms close to carbon were formed into single layers as well. So germanium, silicene, phosphorine, which is black phosphorus, were born, and people discovered very new properties among them as well. So for example, black phosphorus, I'm showing you on the right side, is also hexagonally arranged, but it has a puckered structure, where atomic planes are slightly displaced from each other. So this structure and the atomic the nature brings new properties to these materials, very useful properties. So another thing that we can look at is how does the three-dimensional versus two-dimensional materials behave electrically. So you may recall that electrical properties are well explained through the band theory of solids. So if you go back to atoms, atoms has energy levels. You have your valence electrons and you have the excited states, two energy levels at least, separated by a gap. So you put large amount of atoms to make a solid, typically 10 to the 23 in number terms. So when you do that, all these energy levels merge into bands, and what's known as valence band and conduction bands form, and there can be a gap between the two, and that gap is pretty important for electronic application. For example, if you take one of the very popular semiconductor material, silicon, the band gap is 1.1 eV. Germanium is about 0.7 eV, but it's very much intrinsic to the material. You cannot change that easily unless you do something, change the chemistry. So in contrast to that 3D behavior, 2D materials behave very differently. So a very good example is black phosphorus or phosphorine, where the band gap really depends on the number of layers in the system. So if it's 2 layers, it's a higher energy level. So around this region, 1.5 to 2 electron volts, it's pretty much matches the solar spectrum, for example. So for radiation interaction, so this is very useful. In graphene, what you have is a semi-metal without a band, so it's a gapless material. So this gives another richness into this material class where you can change a lot of things. And another example where they are very different from 3D materials is how they interact with radiation. So I'm pretty sure a lot of people are familiar with, especially condensed matter physicists will be familiar with X-ray diffraction, where you have coherent X-ray scattering from crystalline material. They produce what's shown on the top right is very sharp peaks, which are almost like delta functions. But the two-dimensional materials, when you have the X-ray diffraction or when you scatter X-ray out of those materials, behave completely differently. They're very broad peaks, and also they have their own signature type line shape for the X-ray peaks. For two-dimensional material, there's something called a Warren effect, which create this sawtooth type asymmetric peaks. So that's very very special instance for two-dimensional geometry. So it's a consequence of the dimensionality. So there's a pretty large behavior differences between these materials. So in 2010, I think very exciting thing happened. Andre Geim and Kostya Novoselov, they isolated single atomic layer of graphene. Actually, they did that in 2004, but they got the Nobel Prize. They were awarded the Nobel Prize for this achievement. And I think this is really I think what I consider as a huge triumph for experimental science, because it's such a simple method was used to create a single atomic layer of carbon and show, and these two folks have shown the world that single atomic layer can exist independently. So for a long time, very prominent theorists have been arguing that something like that cannot exist because any thermal fluctuations can destroy the system, according to theory. But undeterred by that, I think Andre Geim and Kostya Novoselov went ahead and shown the world that this is not real. It really does exist. So I think something that we can learn from them is not to take things for granted. Just do the experiment. That's one of the lessons at least you can take. And also you think about how they can do that, considering in a small quantity of carbon or any material, there are about huge number of atoms and you want to go down to one atom. So again, the two-dimensionality of graphite helps a lot. So what they did was they took a graphite crystal and put a scotch tape and kept cleaving them until you get to the single atomic layer. And you clearly understand why this is even possible by looking at this picture, because if you take a single crystal of graphite and use a tape to split it, on average is 50% each side, right? So if you continue this process on and on, you have this 2 to the n power helping you. So if you start with the thickness d naught, let's say about a micron, you need only 10 times to do this 10 times to get to the nano level. So that's the beauty of this technique. And in reality, you can find sub-micron crystals very easily. So you really need to do this about 6 to 7 times to get to the atomic level. So, I think as condensed matter physicists, we have this Avogadro number in our head, 10 to the 23 atoms. From that kind of order of magnitude to do into 1, it is really possible with this simple technique. So it's sort of it's a wonderful thing to witness that as well. And why we are all interested in graphene is its superlative properties, right? So compared to copper, it's really highly conducting. It's the most electrically conducting material. It's most thermally conducting material, and it's the most strong material in the universe. So it has all these superlative properties. So everybody gets excited because now we can think of really very nice applications that we can bring to the world, help our lives, hopefully, right? So there's a lot of well-known properties, but let me show you something not that well-known, something that we found, pretty recently. It's how this two-dimensional material interact with radiation. So if you dump some radiation onto a material, it gets heated very quickly. And the heating rate is really dependent on how fast what's the energy source is. The more energy you have, it heats faster, right? But the cooling is completely different. I'm pretty sure you're familiar with the Stefan Boltzmann law. It's the T to the power 4 dependence. So if you look at a small piece of graphite or graphene, the cooling rate after heating, you can show that easily, is proportional to the emissivity divided by the specific heat per unit area. So if you put that number, that ratio for all the known materials versus the tensile strength or the other way around, you can clearly see that graphene and carbon material are pretty unique. They occupy a very unique place. So hopefully some applications will come out of that capability of this material. So I'm just trying to highlight the uniqueness of this material. And because of these extraordinary properties and the low cost, there are so many potential applications. So Graphene Council, which is one of the large bodies that deals with graphene manufacturers and graphene researchers, put out some good surveys, and they listed all these application area. They range from plastic composite films to water purification, medical application, wearables, to even the best sound transducers. So these are called application verticals, because in each vertical you can have many products. So that's why the whole excitement is all about for graphene. And also the Graphene Council put together this chart, which I use from their courtesy, is something called the Gartner hype cycle. This is valid for any technology or any new material. How the technology evolves is shown here. So in the very beginning, it's the discovery phase, and then a lot of excitement and huge expectation at the peak. And this is the trough of disillusionment, where people get really frustrated. And luckily, we are in the perfect timing for graphene researchers. We are just starting the real world applications now. I think just last year, Ford Motor Company announced that they are putting real graphene into production vehicles right now. And lots of startups have tried to do the real commercialization of the material now. So hopefully we'll be in a nice trajectory from here on. And my company Hydrocraft is also part of this story. You know, we are selling materials for biosensors to do advanced cancer diagnosis, for example. So there's a lot of exciting applications for this new material. So I want to talk about one single application that's impacting our lives, which is the lithium-ion batteries. So a couple of years ago, these gentlemen got the Nobel Prize for discovering the chemistry in lithium-ion battery. Actually, one, I think John Goodenough is a physicist, the other two are chemists. But the important thing is everyone in the audience, including me, uses lithium-ion battery daily for your cell phone, your laptop, and you know it's the most universal energy source right now. So it's really important to our lives. So let's see how we can use graphene in this the device, and what's the physics behind the graphene in that. So for people who are not familiar with lithium-ion battery, it's like any battery, it has two electrodes, anode and a cathode, and then there's some electrochemistry going inside. So lithium-ion shuttles between the anode and the cathode during charge-discharge cycles, right? So there's a lot of electrochemistry going in. But to get what's happening inside the lithium-ion battery to communicate to the outside world, what you need is something called the current collector. In this case, we use aluminum on the positive electrode and copper on the negative electrode. But what happens is these metals corrode very easily due to the electrochemistry. So what you have to do is you have to put protective coatings to make the battery last longer. So in my previous work, I discovered that you can put nanoscale graphitic coatings on aluminum to protect solid state lithium-ion batteries for electric vehicles. So this works really beautifully. You know, I call this material graphene-like carbon because it's not pure graphene, but it's pretty close to graphene in the performance. And it's also close to graphene in the structure. So it's only 10 nanometers thick. And once you put it on aluminum or copper, this one protects the battery and makes the battery last longer and makes the battery lighter as well, because people were using very thick carbon black coatings before that, 100 times thick. So we used to manufacture, develop this product here in London, and we are manufacturing it here as well. So, but to understand what's going on with the system, let's look at the inside of the battery, any battery. So here is a picture of the cathode, an SEM picture. This solid piece is aluminum foil that's about maybe about 15 microns thick. And you can see the active electrode material. In this case, it's known as NMC, nickel manganese cobalt mixed oxide, with a lot of carbon additives to make the electrode conductive. So it's pretty complicated structure. So if you simplify it graphically, this is what it looks like. So you have spherical particles clearly making contact with the planar aluminum. And in a device operation, what you are interested in, the corrosion rate, we want to minimize that. Now, what happens at the interface is the most important one. So corrosion rate, if you think in terms of Faraday picture, is basically what's the rate of electron transfer, which in physicist term is the current density. So the corrosion rate is proportional to the current density at the interface, right? So, and what happens is, let's digress a little bit and look at the current density at any contact. So when you make any electrical contact, we sort of it's our naive thinking is, okay, the current goes really uniformly from one conductor to the other, but the case is very different in real life. So here I have analyzed just a spherical particle between two plane conductors. So if you solve the Laplace equation and calculate the current density, you get a very surprising results. So you see, this is the plot of current density. I'm using finite element analysis here. You see about 4 hotspots in that two-dimensional cross section. So in reality, it's you have to rotate this in the vertical axis. Then what you get is a circle of high current at the electrical contact between the spherical particle and the plate. So it's not very uniform. There's a huge current spike at the interface. So, 80% of the current flows in that region. So now with that understanding, we can look at what's happening in a battery, in the real battery. So if you look at the current collector, now we have this graphitic plate, and this two-dimensional material, nanomaterial, has this unique property in that it carries current in a different rates in different directions. So we call it an anisotropic material. So that's imparted to the material by the geometry and the atomic arrangement, and that makes a huge difference for these devices. So for example, in most of these layered materials, in the XY plane, current is conducted way better than to its perpendicular direction, which is what we call the C direction. So in an isotropic material, that conductivity ratio is 1. So that's why we call it isotropic, it conducts equally in every direction. Whereas in graphite or in graphene, the ratio can be as high as 10 to the 5. So more than 1,000 for sure. So now you can use that property and do the model again. Just a very simple model, spherical particle contacting through an interface, an aluminum or a metal piece. So we do the proper calculation, putting the right numbers through this one. This is what we find. So on the right hand side, I saw in red, without a carbon coating, what's the current density behavior at that nanometer size particle when we use this technique. And obviously we see large variation in the current density. So if you put thick, say, carbon black coating, 20 nanometers, still we see that change. Now, if you put a graphitic coating, nanographitic coating, and in the modeling, you can just vary the anisotropy really easily. When you even hit 100, it becomes very apparent that the current density evens out quite nicely. So as I said before, graphene or graphitic materials has much higher anisotropy. It conducts way better in the XY direction. So what this does is it evens out the current density right across the interface. So if you look at the Ohm's law, the current density is proportional to the electric field. Then what is showing is this graphitic coatings are very effective field spreaders. So that's really the physics behind why it's working so well, which prevents the corrosion. So it limits the potential to that small area that doesn't allow it to corrode. So this is the final slide on that section. Typically, people were using, before this came along, very thick coating, like micron thick carbon black coating at the interface, whereas we can replace it with a very clean interface now, both chemically and electrically very clean interface, which makes the battery work better. But now we understand why it's better as well. So I think let me turn now into graphene, real graphene, and talk about, actually, let me talk about one more application, that is the graphene's optical properties and electrical properties. So when we have a single graphene layer, one atomic layer, the optical absorption is about 2.3%. So when you stack them more and more layers, it absorbs more, as you can imagine, and which means the optical transmission gets lowered as well. And at the same time, when we add many layers to make a multi-layer system, resistance also decreases. It becomes a better conductor. So now you have a tunability of these parameters. So one application we developed using that property, or both properties, is a solution for semiconductor industry. Over the years, the semiconductor chips have become smaller and smaller. Here I'm showing you at scale beside an ant. This is the tiny semiconductor chips packaged in a small pocket here. So when they become smaller, it becomes harder to handle in large scale, because when people assemble circuit board, this is done through automated machinery with machine vision. So they have to take this out, the microchips out of the packages, which are plastic, and that creates static electricity, and that static electricity can damage the microchips, or they can just, basically they just fly away because of under the influence of the electric field, right? So it's hard to control. So anti-static coatings becomes very important in this industry. So typically people use metallic coatings, which is not the greatest for the environment. So what we did was we put 15 nanometers of this graphene-like carbon material, and you could tune this static decay. For static decay, you need the right resistivity of the material, but the machine has to see optically, it has to see through the packaging to identify the microchip. It has to read the barcode. So you compromise a little bit on both the properties, and you can make a very nice anti-static coating using this. This is a commercialized product as well, using graphene-like material. Okay, now we turn into graphene manufacturing methods, because it's pretty interesting. So we know graphene has very unique properties, but how do we make graphene? So that's sort of a interesting question. And there are two main areas, techniques. One is called the top-down method. The other one is the bottom-up. So the top-down, you can understand, the parent material is graphite. So you start with graphite, and graphite is very common. And it's very, I think in Sri Lanka, graphite is pretty well known. One of the best graphites found in Sri Lanka, right? So quality-wise. So top-down is a very interesting technique as well. So you can do, obviously the Nobel Prize was awarded for the using the Scotch tape method, but you cannot do manufacturing with that scale up. It's not really possible. But there are a lot of other measures like chemical exfoliation and electrochemical exfoliation or photo exfoliation, those kind of things. And the other one is the bottom up, which is very interesting, because you start with the carbon precursor material and do some chemistry and make graphene. So this is building atom by atom type thing. So both of these has advantages and disadvantages, but it's very hard. What people have found is it's very difficult to scale up and to bring this up to the industrial level. So I think last year, again, the Graphene Council asked, they conducted a survey and asked people, what are the major barriers for commercial adoption of graphene? The three top factors were the cost and the production method or lack of production method, the inability to scale up, and the consistency of manufacturing. So luckily, we've, at Hydrograph, we found a really nice manufacturing method invented by Chris Sorensen in the physics and astronomy department at Kansas State University. What Chris did and his team did was, they, instead of doing a lot of chemistry, these are physicists, so they went for a very simple, elegant technique. They took acetylene and oxygen, put it in a small chamber, and used an automotive spark plug to spark detonation. So the energy input is so tiny, just a electrical spark. This makes this combination of material explode, or what you call the detonate. And it's such a quick process. Within 15 milliseconds, the reaction is done, and out comes graphene. The whole chamber is full of graphene. So it's a very elegant, beautiful process, and it's really easy to control. And the one very important aspect is the energy input is very negligible, because all the energy comes from the material itself. the internal energy stored in the material. So it's a extremely clean green process, and what you get is a new form of graphene in the purest form. So we don't have to use any catalyst like what people use for carbon nanotube manufacturing. There's no catalyst. So this is called the synthetic detonated graphene SDG, and we've been working with Chris and his team for a while now, and this has been scaled up right now for manufacturing. And here's a picture of Chris standing very proudly with the detonation chamber. This box is the electronic control for all the gas flow. So this is a fully automated system, and this is Harold Davidson, who's my CEO at Hydrograph. He's the guy who funded all this research. So I think two very important people. And what's more important, I think, is this technique is so versatile. So instead of acetylene, if you take methane, which is very common biogas, put it with oxygen and detonated in the same chamber, what we get is hydrogen and carbon monoxide. So this mixture is known as syngas. We can use this as a fuel source by itself, or we can separate the gases using a membrane separation, which is well known in the industry. And now we have a very economical green automated process for making hydrogen. By far the cheapest method of hydrogen production in the world. If you think of, so the next economy, the sustainable green economy that we want to have will be partly based on graphene and partly based on hydrogen. There's a lot of big companies are working on hydrogen solutions right now. The fuel cells, automotive industry is looking at, Toyota is commercializing cars driven by fuel cells powered with hydrogen. So because it's the cleanliness, because of the greenhouse effects, that the global warming aspects of the fossil fuel, we want to get away from that. So these two materials will help tremendously, we hope. So hydrogen is a commodity right now, whereas graphene is on the other side, is a very new material that can do a lot of new things. So pretty exciting space to be in. And here is one of our grad students scooping up graphene from the experimental chamber. Just in taking some scoop, you can see the graphene in bulk form. So this is a pretty unique production method. And this is our production device. As you can see, it's a little bit bigger, but tiny compared to a lot of industrial process. So the footprint is very small. Either we can control it remotely, completely decentralized production, or we can have many of these units in a centralized location as well. So it provides very multiple approaches to the manufacturing. So as I said, this form is pretty interesting, this graphene in bulk form, because it's very low density. So if you take this material, what Justin is scooping up, put it into an electron microscope, this is what we see. So on the right, at a low magnification, it's a sponge-like structure. So this is a hallmark of a fractal. What happens is, since this is a gas phase, reaction happens so quickly, and graphene particles, tiny nanoparticles form, and they keep aggregating until it spans the whole chamber. You okay there? Do you have any questions? So yeah. So, and as you can see, this is known as an aerosol gel because so I think this is a new form of graphene. For all the other graphene made in different techniques are completely different morphology. So this has its own potential to do different things. So this is my last slide. So very recently we opened a R&D laboratory in London that we started to do some application development with hydrograph. So if you look at the graphene, we can think about, I think, bulk powder, so we can make composites, for examples, or we can go to ultra thin coatings to do battery materials or other sensing material. So that's where we want to go next. Hopefully, in a year's time, I can give give more details about the applications later, but that's the story we have right now. And thank you so much for your attention. And I like to thank my previous employers as well as Kansas State, our colleagues and Hydrograph for letting me do this work, and for Professor Gamage and Dr. Chaudhuri for organizing this. And thank you so much. And if you have any questions, I'll try to answer. Thank you so much.
Thank you, Dr. Divigalpitiya, and so for the nice presentation. And the forum is open for any questions. Yeah, I will ask the question. Can you use the chemical vapor deposition methods to deposit thin films? How controllable will it be?
Yeah. So people they do use chemical vapor deposition, CVD technique for making graphene nowadays. And
can you control the film thicknesses?
Yes, you can. So, but one of the issues is, it's a high temperature process. You need a lot of energy, but you can make thin films. It's very good for thin film applications. But what has stopped the wide adaptation of that process is it creates a lot of defects. So that's where the technology is, which is pretty common in this field now. So it turns out, so very strangely, detonation graphene is very identically similar to CVD graphene. So you can. I don't. Sometimes you get surprised. Some people say, yeah, that makes sense, but anyway, that's what it is.
But the detonation method, you cannot make like thin films, no? Just giving the
no, we don't deposit films. No, you're right. Yeah, you don't deposit film. It's an aerosol, so it's a gas phase reaction in the gas phase itself, not on substrate. So this is not good for depositing thin films, but it's good for making bulk graphene samples. Good question. Yeah.
Yeah, just another one question. So I'm interested of the graphene magnets. So what is the current situation of the graphene magnets? So do you have the
graphene market?
Magnets, yeah. Graphene magnets, yeah.
Well, sort of. So graphite is a diamagnetic material. There have been very cursory studies, but I haven't seen anything that sticks out. Do you like to share anything with the audience? Because I'm not aware of any interesting development lately, though.
Okay, so just to realize something new going with that area. So that's why I asked from you that it's okay. So,
okay. Yeah.
Okay, so if there are no more questions, we can go to the vote of thanks. I will be doing the vote of thanks. So on behalf of the Institute of Physics Sri Lanka and the committee which organized this presentation or this guest talk, I greatly thank Dr. Ranjith Divigalpitiya for devoting his time for giving us this interesting talk and giving us some good information, briefly explaining the things about these 2D materials and the developments of the graphene technology. And I also thank the organization committee for organizing this event, and I also thank all the participants for participating at this event. And also there will be another such event next month, so I hope also you will participate in that. So I take this opportunity to thank again Professor Divigalpitiya for this for his time and giving us this important talk.
Thank you so much. Yeah. Well, take care then.
Yeah. So thank you very much for everybody, and so I will end the session.
Thank you. Bye there.
Stay safe.
Bye there.